Hello, and welcome to today's Safety and Health Webcast, Innovative Technology for Confined Space Safety, sponsored by Draeger Safety. My name is Kyle Morrison. I'm the Senior Associate Editor with Safety and Health Magazine, and I'll be moderating today's session. Thank you for joining us. In a few minutes, we'll start the presentation, but first I'd like to go over some housekeeping items. The views of the speaker and his organization are his own and do not necessarily reflect those of the National Safety Council or Safety and Health Magazine. Mention of any commercial enterprise, product, or publication does not mean the Council or the magazine endorse them. At the end of today's webcast, we'll have a question and answer session. To ask a question, simply type in the text box located in the lower left-hand corner of your screen, then click the Submit Question button. Feel free to ask your question at any time during the presentation. You don't have to wait for the Q&A session to begin. We'll try to answer as many questions as we can, but due to the large number of participants today, we may not get to all of the questions. However, all unanswered questions will be forwarded on to today's speaker. For basic troubleshooting information, please click the Help button located on your screen. At the end of the webcast, you'll be asked to complete an evaluation survey, and I'll talk a little bit more about that after the presentation. This webcast will be archived for 3 months, so you can access it after today's live presentation. Within about a day, just return to this URL to view the archived webcast. With that, I think we're ready to begin. Our speaker today is Rob Zurich. Rob is the Marketing Manager of Oil and Gas and Chemical Segments for Draeger Safety. Rob?
Thank you, and good morning to some of you. Good afternoon to others. It's high noon here in Houston, Texas. So thank you very much for making the time to join us this afternoon. Many thanks to Safety and Health Magazine and the NSC for giving us this opportunity to speak to you today. Throughout today's presentation, I'm going to obviously get to the idea of what innovative technology in confined space safety means. And you'll see as I go through some of the information today, which includes a lot of basic yet probably not necessarily widely known information about confined spaces. So it'll be a good opportunity to refresh some memories and also bring some other issues to light. But going through some of those issues, you'll also see how it all ties back to some of the innovative technology that, with good reason, Draeger has spent a lot of time looking at and innovating new products to make sure that safety in confined space is never less than perfect. So without any further ado, let's dive right in. And really the best place to start is kind of back to basics and defining what a confined space is. And so the textbook definition of confined space is that it's an area that's large enough and so configured that an employee can bodily enter and perform work. This space would have limited or restricted means for entry or exit, and it's important to know that it's not designed for continuous employee occupancy. So frankly, I mean, by that definition, confined spaces can be any of a number of different kinds, and that's not necessarily inclusive of industrial situations. But then we get into something called a permit-required confined space. And that is where, in an industrial environment, a safety specialist would need to issue permits to allow an individual, a worker, to enter a confined space. And a permit-required confined space has one or more of the following characteristics. It has the potential to contain a hazardous atmosphere. It contains a material that has the potential for engulfing an entrant. It has an internal configuration such that an entrant could be trapped or asphyxiated by walls that inwardly converge, or a sloping floor tailoring to a cross section. So again, somebody might be unable to climb back up to a higher point, or would slip and fall and things like that. And finally, a permit-required confined space would include any other recognized serious safety or health hazard. So when you get into any one or more of these situations, that's when a permit would be required for a confined space, and that's typically what we most of the time, certainly at Draeger, and I suspect for most of the audience today, has more experience with more industrial type environments with regard to confined space. So once we define, again, what a confined space consists of, as the textbook says, we can start then thinking about what type of hazards exist therein. And, frankly, we can talk, we probably could talk, I should say, for hours on the various types of hazards that exist within a confined space. So I won't get into all of them, but just to give again, that basic overview, some of the hazards can be atmospheric in nature, so you'll see an O2 deficiency or an enriched O2 environment, which then becomes explosive. You can find other atmospheric hazards such as combustible gases, toxic gases. In certain environments, certainly agricultural environments, you'll see combustible dusts, but obviously that's not limited to agricultural environments. There are also physical hazards that come into play in a confined space, and those can involve engulfment either in a gas or a liquid, entrapment in terms of either being stuck in a space or unable to escape. So again, these are just really off the top with respect to the types of hazards that exist within a confined space, but those could be any combination of those ideas, or it could be completely different. But the bottom line is that there are myriad hazards when a confined space is brought into play. Typical reasons for entering a confined space, again, some of these are obvious, some might not be, but again, I think it's important to kind of reiterate some of these to at least set a baseline for our discussion today. But people will enter a confined space to clean. They'll enter a confined space to inspect the physical integrity of a tank or something of that nature. They will enter to maintain, to blast, to surface coat. They'll enter to repair and install equipment, varying types of equipment, of course, but some of those examples would include valves, pumps, piping, etc. There'll be adjustment and alignment of mechanical mechanisms within a confined space, and things even as hazardous and by bringing into the equation electrical risk, but electrical transmission cables. All of those things tend to be installed and exist within confined spaces, and will also add to the reasons for entering. So now that we've got that baseline set, I think we can take the next obvious step, and that's to get into the examples of confined space. And again, this is literally the tip of the proverbial iceberg, but confined spaces can exist in storage tanks, sewers, boiling rooms, manholes in an urban environment, ship voids when we're talking about maritime work, in tunnels, excavation situations, pipelines. So if you're looking at a petrochem or an oil and gas environment, obviously those can occur at the midstream level as well as the downstream level within a refinery. Trenches that exist for various types of industrial work, pits, silos, vats, wells, wing tanks. Again, there's really no limit to the types of confined space that exist in an industrial environment, but the key is really just to pay attention as a worker, as a safety conscious individual, of all of the various types, to make sure that nothing is being left out and nothing is being ignored when it comes to confined spaces. The other thing to point out here is that in the United States, any pit or trench of greater than 4 feet from entry is classified as a permit required confined space as well. So that's an important thing to differentiate a ordinary non-industrial, non-permit required situation with one that will require a higher level of safety, if you will. So we know that, again, these confined spaces will be in a number of different places. There will be need to enter for a number of different reasons, but we obviously want to do that safely. And in order to do that safely, we need to be concerned with atmospheric testing. Typically, what we'll do with regard to atmospheric testing is just a basic gas monitoring, which will minimize the serious or the chances, I should say, of serious injury or death in this type of situation. And it's also important to make sure that that type of atmospheric testing, that type of gas detection is done with a properly tested, bump tested, and calibrated instrument prior to use. It's really the only sure way of knowing if dangerous gases are present. So if all of the safety protocols around a particular type of gas monitor are not followed, certainly there is a very high risk of inaccurate readings and thereby putting a worker at risk. So when you get into the situation of atmospheric testing, again, the first step is making sure that a gas monitor is properly tested and calibrated. And once that point is established, there is the question of when and where to sample. The whens will be prior to entry. They'll be continuously during entry. So while a worker is within a confined space, we want to continuously monitor for hazardous atmospheres. And we'll also do it prior to re-entry. If someone were to leave the confined space and re-enter, we want to make sure that we recheck it before that's done. We will also be concerned with the wheres, and that's in different places within the confined space. We need to be very aware of monitoring in each area, in each strata within the confined space. And the reason we do that is because of gas stratification. There's different molecular weights. There's different gas mix that can exist within a confined space. Some gases are heavier, some gases are lighter, and will gravitate toward the bottom if they're heavier, obviously, and move toward the top of a confined space if they're lighter than air. And some will maintain the same weight as breathable air and oxygen, so they'll be in the middle section of a confined space. So we do need to be very conscious of the fact that we take those readings at various intervals, not to exceed 4 feet, in order to make sure that we are, taking into account the various stratification that can occur in many cases without our knowledge. Again, the other reasons, in addition to just molecular weights and the weights of different gases, obviously we do need to be concerned with things like flash point. So that's something else that a characteristic of gas to be concerned with. We need to be concerned with the pressure. We need to understand if there are any color variances or odor characteristics that we can be aware of in order to understand what is present in a confined space before we enter. So those are other things to pay attention to. And obviously, the bottom bullet point that's on your screen right now, again, maybe that's obvious to some people, but it's interesting in our conversations with various people in various industries that Draeger services. Some of these idiosyncrasies of what we consider to be the basics are not necessarily widely known. So even something by clarifying that not all materials are detectable by sight, smell, or taste is an important thing to mention in order to maintain the utmost safety in a confined space. You have to monitor. You have to have that perfectly calibrated and tested gas monitor to ensure that any readings are accurate and you're not missing anything because you're relying on sight, smell, or taste. So historically, then the next step in this process of seeing kind of from whence we came with respect to confined space technology is to look at historically how we have entered confined spaces and made sure that they're safe for entry. Typical pre-entry testing was and still is conducted with oftentimes a gas monitor with some sort of a probe or a float that's done from the outside looking in to ensure that the readings are within an acceptable range. Once the space would be deemed safe from that initial reading, a worker would wear a monitor during the entry or we'd see a monitor hanging into the confined space or placed nearby to maintain sampling during the entry. So again, obviously we would want something to be available on the worker, but we'd also want to have something nearby to alert them if anything were to happen. Typical issues with these techniques, and again, typical issues still exist with these techniques where they're used, is that if something's left on the side or even in the bottom of a confined space, it could get splashed, it could get covered with some sort of a material, it could be accidentally damaged. There are issues oftentimes with the audible alarms and whether or not they would be heard by someone within a space, if it's alarming outside or if there's other ambient noise in an industrial environment. In some cases, different monitors or different alarming mechanisms would also include a flashing light that might be obscured if it's, again, outside of the sight lines of the worker or otherwise obscured by something at the work site. So in spite of the fact that these precautions are taken, there are still a lot of risks associated with the traditional gas monitoring that exists with entering a confined space. And unfortunately, because of some of these limitations, there have been some bad things historically happening with confined space entry. Between the years of 92 and 2005, there were an average of 41 workers killed every year due to confined space-related accidents. A lot of those, again, had to do with just basic human error. Some of those had to do with faulty monitoring and some of the reasons that I just described with respect to alarms that were not heard, were not seen, or malfunction. But unfortunately, something else that might not be immediately evident to everyone is that rescuers are often among the fatalities with regard to a confined space incident. And as a result, 1/5 of confined space incidents result in multiple fatalities, according to a study in 2006. And then also for every fatality due to oxygen deficient or toxic atmosphere, 2 non-fatal injuries occur, one of which requires hospitalization. So again, these are very, very sobering statistics and issues that occur when something goes wrong in a confined space. And I think the one thing that is true and kind of that universal truth is that something will go wrong eventually. And knowing what to do when the time comes is very important. Because even if a worker is properly trained, an attendant or someone else on the work team is properly trained, they tend to forget proper entry procedures during an emergency because they're overcome by their natural emotion to rescue a coworker. So in spite of all the precautions that are taken ahead of time and the training that might exist, it still might not be enough because of these natural emotions that occur when someone wants to rescue a coworker. From those years of 92 to 2005, there were 431 incidents resulting in 530 fatalities, the majority of which the majority of those deaths occurred due to oxygen deficiency. So it wasn't even a matter of combustible gases in the majority of those cases, although again, combustible gases then again becomes the second leading factor in those deaths. But I think that's an important number to point out is that there aren't necessarily these, red flags going up knowing that it's a purely toxic environment. Oftentimes it's something as simple as a lack of oxygen that causes one person to have an issue in a confined space and for, again, an attendant or a coworker to then succumb to the same issue. Similarly, again, if we look at those deaths by job type with those 431 incidents and 530 fatalities, again, we'll almost see an exact parallel between the actual work being done, which is repair, maintenance, etc., and the rescuers. So you see a 40% to a 36% difference there. So it's almost identical, which really reflects the story that we just, or I should say the examples that we just used. And again, in spite of everything that's done, oftentimes it's still not enough. And This is a case study that came from a NIOSH example that occurred in an urban environment where someone had gone into an outdoor vertical manhole, and they did the pre-testing according to the standards that we described earlier, with some probe testing and making sure that the environment was okay to enter. It was acceptable conditions. The worker went into the space, and the weather around them got a little bit worse. So the hole watch attendant, decided to go into a vehicle that was parked nearby to seek shelter. Well, unfortunately, within the confined space, conditions deteriorated, and as a result of that, an exterior monitor went into alarm. Unfortunately, because the person had gone into the car to seek shelter from the poor weather, they didn't see the flashing alarm, they didn't hear the alarm, and their inability to recognize this prevented the attempt watch person from notifying the entrant. A combustible gas built up to explosive levels. There was an explosion, and the person within the confined space died. So you can see that in spite of those precautions that were taken prior to this situation happening, it still wasn't enough to prevent a fatality. And that leads us really to kind of talking more and more about what makes an effective product or process for safe confined space entry. And again, all of that background kind of leads us to some things that we know then would make a difference. One, that we want something that's flexible. And by flexible, we don't necessarily mean it can bend and be shaped into different things, but we want it to be able to be used in different ways. We want a monitor that's not something that's meant to be worn on your lapel to be set to the side of a confined space and trust that that's going to do the job. We need something more robust than that, and we need it to be able to do more than one job accurately. We want it to be portable, and we want it to be scalable for different types of jobs. So again, as I say, whereas a typical single and multi-gas monitor is certainly portable, it's not necessarily scalable. You can't set a bunch of personal monitors around a confined space and hope that that's going to do the job. We want something that's going to have a long battery life. It's not going to give out after a certain number of hours, or perhaps if it hadn't been charged properly the night before during a confined space entrance. We want it to be able to stand by and be on guard the entire time. We want it to be durable, so it's not affected by any corrosive liquids, gases, the weather, and we want it to have highly visual and audible alarms. And the other piece is to have something that's classified for a hazardous location up to and including zone 0, which is, again, where you get to start talking about explosive environments and extended periods of time within an explosive environment. When we talk about flexible, another aspect of flexibility means that it allows for easy sensor substitution. So if the conditions within or near a confined space change, we want to make sure that we can change out the sensors, change out the mechanism of the monitor to ensure that it's detecting for the gases that are present in that environment. And we also talk about the ability of something that's portable, as I said, to be moved and deployed quickly in any environment. And we want something that's pretty robust in terms of what it can withstand. I mean, how many times has an instrument been dropped down into a hole or kicked off a ledge in some way because it either wasn't bolted down, it wasn't heavy enough to at least be somewhat inerted to the surface that it's placed on. So we need an instrument that again can withstand a little bit of punishment in these industrial environments. We want the runtime and the battery life that we talked about. Typical personal monitors can run 10 to 12 hours at most, and again that's when they've been either charged correctly prior or after a job, or they have fresh batteries in them. but again, experience would say that that's not always a given, and mistakes are made. So we want something that can be ensured to run for an extended period of time and crossover shifts to make sure that even during a shift change, a worker entering a confined space or near a confined space is protected. So you look at something that nowadays we can count on instruments to have up to 120 hours of run time on a single battery charge. And those type of products do exist now as part of the new technology that's being innovated. We want something that's durable, I mentioned, but we also want it to be water resistant so it can withstand just basic weather-related wear and tear. We want it to have a certain level of IP protection, up to IP67 if possible. We want it to be loud so that if it alarms when ambient noise is high and loud and equipment is running nearby, we want to make sure it can be heard when it goes into alarm. We want to make sure that there is better visibility of any sort of a flashing light that would alarm so that it can be seen in a 360-degree environment by anyone who is working around it. So again, we've learned our lesson as an industrial safety group, team, audience, what have you, across the board. Historically, we know the limitations of a typical portable monitor, and therefore that allows us to understand that something more is needed. So we need these 360-degree lights and 120 decibel sweeping audible alarm. And we want it to be able to be communicated with other units, both inside and outside the space. So in situations where we have wireless communication that can be viewed by an attendant, can be viewed by other workers that are nearby, regardless of outside conditions or machinery that's running, that's the other advantage that exists in modern technology, that it gives us the chance to have things that can communicate through walls, inside and outside of a confined space. And all of these things, all of these advances or these ideas literally make for a safer environment. And I think that, of all things, is the most important thing. It's not technology for technology's sake so that you can play a game on your mobile phone while you're waiting for your flight at the airport. These are legitimate reasons for creating a safer environment as it relates to confined space, and it's based on all the reasons we discussed earlier in the presentation. And so when we talk about, again, the wireless communication and the volumes of alarm and the visibility by an attendant, those are all things that have been dictated by events leading up to this current day with respect to confined space. So, it is important to then say, okay, zone zero, and this is another topic that may be familiar to some people, but in other places where there isn't a lot of explosive environments, it might not be as well known. But zone zero provides the highest level of intrinsic safety, which means something's not going to explode. That's what you want to have in that type of environment, in a zone zero environment where explosive air gas mixture is continually present for long periods. You need to have something that can sit in that environment and do all the things we just described so that if there is a buildup of combustible gas over time, it's not going to affect the availability of an alarm or alerts to ensure someone is aware that a dangerous environment exists and they need to remove themselves from that confined space. So again, I will say that obviously as a Draeger employee, I look at this situation through our own lens, and certainly I will say that the products or the ideas that we've described today are encompassed in something like our X-Zone 5500. We talk about this being something of a portable fix system, if you will. It's something that's durable. It's something that can be easily deployed, put together through a wireless fence line to create safety perimeters in not only confined space environments but elsewhere. It's got an incredibly loud alarm. It's got a highly visible 360-degree visible flashing when monitors go into alarm. It's deployable in zone 0. Again, for all the reasons we've talked about today, this is really what technology has dictated we do as safety product manufacturers to ensure the safety of our of those that enter confined spaces in oil and gas environments, in other industrial situations, in mining situations, in fire and hazmat situations. There really is no end to not only confined spaces, but areas where a wireless fence line of some sort is going to make a huge difference in the safety of the employees that exist there. And for those reasons and for all the reasons we talked about today, again, that's what we have engineered into this product. But I also will say that there are plenty of other options that exist today with respect to setting up a better and safer confined space environment if you pay attention to even just the bullet points that are on the screen now. Have something that's transportable, make sure it's loud and visible when it alarms, look for zone 0 approval, find something that's wireless. Again, something as simple as that, lacking in wires being laid around a job site is going to make someone safer. You want something that's flexible and can be changed out depending on the different hazards that might exist in an environment. And you want something that's easy to maintain. So if you keep all of those ideas in mind as you're looking for the correct type of instrumentation within a confined space, you're going to be that much safer. Your workers are going to go home safe at the end of the day, and that's really at the bottom line with respect to why we do what we do. We want everybody to go home safe at the end of the day. So that actually concludes my part of the presentation. But at this point, I'm excited and hopeful that I can answer some additional questions.
Excellent. Thank you for that wonderful presentation, Rob. Before we start the Q&A, I want to remind everyone of the evaluation survey we're asking you to complete. The survey should be appearing on your screen now, and we ask that you consider completing it to let us know your thoughts. Your input is important because it directly improves future webcasts. So I hope you do take the time to fill out the survey. If you don't see the evaluation survey on your screen, please make sure your pop-up blockers are turned off. All right, Rob, let's get to some questions here. With regard to testing a confined space, you had mentioned testing prior to reentry. Why would you want to test prior to reentry if a worker's already been in that space?
Yeah, this is something that it's a very, elementary answer and a basic one. But interestingly, oftentimes some people tend to overlook simple things like taking a break for lunch or having to use the restroom, coming out for a drink of water. There's really minor things that can occur during a confined space entry that people aren't paying attention to, the fact that even for just a couple of minutes, the environment can change. So even if you come out for any reason at all, it's important to recheck before you go back in, because you really have no idea what's going on in that confined space in the time you're gone, even if it's for just a couple of minutes.
Okay, great. Thank you. What are typical acceptable levels of a gas to pay attention to when entering a confined space?
Well, I'll start by saying there's a lot of different types of toxic gases that you're going to find, and frankly, those acceptable levels are going to be highly dependent on gas type. So again, that's another topic that I think we could discuss for hours and hours. But again, that's just something you need to pay attention to prior to entry, making sure that you're aware of your environment. Other things like oxygen content, you want to make sure that your levels are above 19.5% oxygen and below 23.5%. So that kind of keeps you in a comfortable area between too little oxygen and too much. And then with regard to combustible gases, you want to stay under 10% of the LEL, the lower explosive limit. That's crucial to making sure that environment is safe. Again, the idea of paying attention to it is one thing. The other idea is to make sure you're taking appropriate steps when something outside the acceptable limit is found, and I think that's the other thing. So if you see something that doesn't fall into those lines, then obviously you don't want to enter that space.
Okay. What you mentioned combustible gases. What are some examples of combustible gases to be aware of in confined spaces?
Yeah. Just there's a laundry list. I mean, I can start by saying methane or natural gas. That LEL is going to be about 5% by volume. Propane, pentane, butane, hexane are other combustible gases, in addition to things like methanol and hydrogen. And again, the LEL is going to be a little bit different in all of those situations, ranging from you can have up to 6% of methanol in an environment, and you can go something like hexane where the LEL is only 1.2% by volume. So it varies quite drastically, but again, that's just some of the examples of combustible gases that would exist in typical confined spaces, if you will.
Okay, great, thank you. Now one of the examples you gave of a tragedy is that bad weather that moved in, and the outside observer moved to a vehicle and was far away from the confined space area, and that led to that confined space worker dying. What should be done in kind of a different situation if the entrant asks for tools that are not next to the attendant, but say in a toolbox, 200 feet away? What would be the best course of action in that situation?
Well, again, the best course of action is to ensure prior to entry that any possible tools that would be needed throughout the course of the job are present at the job site during that time. I mean, truly an attendee should not leave that hole for any reason. They need to be there to protect the person that's inside and doing that work. So, again, the best prevention is good preparation. Obviously, again, if you're talking about having to leave to go 200 feet away, again, I go back to looking at it through the Draeger lens and talking about something like our X-Zone product. So if you have an X-Zone within the confined space and have one outside of the confined space, those two X-Zones are speaking to one another. And so if inside the confined space something were to happen and cause an alarm to go off, it would be audible and it would be visible by the person outside, assuming they've only gone 200 or so feet away. So you'd hear it and you'd know something would be wrong immediately. So again, if that cannot be avoided, the key is to make sure that you have an alarm system that's outside, that's visible and audible, that's doing a good job monitoring exactly what the person in the space is experiencing at that time, so you can react immediately if something goes wrong.
When I think about confined space tragedies, one of the stories that always pops to my mind, are cases where the entrant becomes unresponsive and the attendant goes down to save the person, and then they become a victim as well. So what is required for confined space rescue during an actual job? What should occur in that event?
Again, the correct assertion of what has caused the event is crucial. So again, if you're able to get a correct reading off a monitor that's present at a job site, you should be able to know if it's an oxygen deficient environment, if there's something with respect to a combustible gas. Obviously, if it's a situation where it's simple, and I don't mean to make it sound like it's too simple of a thing, but if it is something as simple as oxygen deficiency, you would be able to get a reading off of whatever monitoring system you have set up at that job site, and the expectation would be that any rescuer would be conscious enough to take a look at what that reading says, know that they have to put on some sort of supplied air breathing apparatus before they go in to attempt rescue. And again, that philosophy would apply depending on any other hazard that might be apparent. If you're getting within a LEL, you're going to need to, again, take appropriate steps to either call the person out of the confined space, or if for some reason they need help, obviously put on the correct PPE to get them to go in and get them out. But really, it's just a matter of, again, pausing for a second, understanding what the situation entails. Again, if it's a matter of putting on the right type of PPE, supplied air breathing apparatus, or even some sort of a filter where there's oxygen present, again, those steps just need to be taken prior to somebody going in. There's no question you have to act fast in a situation like this. And I'll also use the example of saying that in some situations, a whole watch person might not be qualified or expected to perform any sort of rescue. They will need to contact either by radio or by some other means a rescue team to come in that is equipped appropriately to go into the confined space to make the rescue. So again, the bottom line is just understanding what the situation entails and then making the correct decision based on what those criteria are.
Okay. So just to clarify, it is okay to rely on local fire rescue for confined space rescue, correct?
Oh, it certainly is. It certainly is. Yes, of course.
All right. Would you advise employers in that situation to contact their local fire departments to let them know that kind of the work they'll be doing on site and just kind of give them a heads up in case something goes wrong?
I don't know that we can necessarily advise anyone to do that. It's certainly something that's not harmful in any way to let a local fire brigade know. And certainly there are some industrial environments where there are on-site fire brigades that are always going to be aware of these situations and this work that's being done. So while again I can't say that I necessarily advise that, it's never a bad thing to let people know what is going on, and if a certified and capable rescue crew is available in any of these situations, it's far better than somebody just making a split decision to go in without thinking the situation through entirely in the first place.
Okay, great. At the beginning of the webinar, you talked about the differences between confined space and permit-required confined space. What level of training should be provided to a contractor who doesn't anticipate their employees working in a permit-confined space, but does anticipate they'll be encountering work and working in non-permit confined spaces? Is there much of a difference in training?
Well, in all seriousness, there probably should not be. Obviously, you're going to have a higher level of oversight in a permit-required confined space. But the fact of the matter is, the same issues can occur even if it's not a permit required. Even in a low-lying area, you wouldn't necessarily have a permit-required confined space, but somebody could be overcome by a very heavy gas that tends to accumulate there. So again, the level of training obviously should be equated to the hazards that exist within a given environment. And if it's a matter of any types of hazardous gases being present, any sort of potential for oxygen deficiency, any sort of potential for explosive gases having exposure to that, the training should really not differ depending on whether it's permit required or not. It's really because the same hazards can apply, just in a slightly different way. So the training should be always at the utmost, if at all possible. And again, I think what's interesting as we've gone through our lives here as a safety company, it's very interesting to see the relative lack of knowledge that exists in certain situations with regard to hazards that can be present. I think in most cases there is a very basic understanding that yes, this is environment X with confined spaces could be hazardous, and we need to be careful and take the appropriate precautions. But I don't know that it's necessarily understood how severe some of these things can be by a typical workforce. And so again, I think that reiterates the idea that the highest level of training that's possible is best, regardless of it being a regular, a permit-required confined space or one where a permit is not required. The safety training and the safety information that can be garnered through just a basic level, or I should say a non-basic level of training, could be something that someone can take through their lifetime and through their entire career, and it can make a difference down the road.
Okay, great, thank you. You mentioned about how trenches 4 feet deep could be considered confined spaces in some situations. We had a lot of questions on that. I was hoping you can go into a little bit more detail about when a trench would be considered a confined space or a permit-required confined space.
Yeah, the definition there, and I'm sorry if I wasn't as clear as I should have been there. Anything greater than 4 feet in depth or in ingress will be a permit-required confined space. Anything less than that would not be. So if you have to go into a space that's greater than 4 feet deep or wide, then it becomes a permit-required confined space.
Now, does that include situations like trenches or excavations as well?
It typically, yes, but again, that actually might be something that varies from job site to job site. I honestly, I don't know for certain. That's a very, very good question, and my understanding was that it was, but again, if it's an exposed low-lying area, for example, I'm not certain that permits are required all the time, but that's something I'm happy to actually get a more specific answer and respond to the entire audience if I could.
Okay, great. Now, that's not to say, again, kind of going back to your point earlier between confined and non-confined space, that's not to say that you know, an area that's 3 feet deep possesses no dangers. It could have the same types of hazards as an area that's 5 feet deep, correct?
Oh, exactly. And that's where, going back to what I mentioned a few minutes ago, I mean, again, the level of training really should not differ whether it's a permit required or not permit required, because something 3 feet deep, again, could, if somebody's lying on their back in a 3 foot deep trench somewhere, you might see the accumulation of some sort of a hazardous gas. You might see hydrogen sulfide accumulate in that ditch, and suddenly, without even realizing it, somebody starts to become sick and ill, and there's an incident on your hands. So, no, without question, that still requires just as much caution and just as much safety precautions ahead of time than something any deeper. It could be 100 feet deep, but something 3 feet deep could be just as hazardous if the right steps aren't taken to be careful.
Okay, great. Now, when we were talking earlier, or rather when you were talking during the presentation, you mentioned how long certain monitors should have a lifespan for in terms of their use before they need to get recharged. 12 hours for personal gas monitors. With regard to that type of technology, how often should gas monitors be bump tested during a confined space entry that may last for as long as 8 or 12 hours. Additionally, should you have rotating monitors or rely on the readings or rely that the readings are accurate from the bump tests?
Well, yeah, really, the question is twofold, or the answer, I should say, is two-stepped, and it's all dependent on the first one, and that is to say that a bump test should be performed before every shift. So anytime someone goes in to pick up a monitor, the expectation should be that the battery is fully charged and that instrument is either bump tested by the person using it or by some sort of attendant to make sure that it is working properly prior to a shift. When you talk about it, whether or not there's a rotation of instruments, there's no good reason to be swapping out, and again, I'm not sure the nuance of the question, but if you're in a situation where you've got multiple instruments on your person and you're kind of taking one off or setting one to the side and having it with you as you go, there's probably no problem with that as long as they're both been bump tested prior to the shift. But the best medicine is to ensure that every monitor is either just coming off of its charging base and being bump tested prior to somebody walking out onto a job site with it. That's the only way you're going to know if it's working correctly. And again, that's not necessarily something. It's something else that we found that isn't necessarily common knowledge. That a lot of people will go, a few days without bump testing something. But really, you should do it daily. It doesn't need to be calibrated every day. Again, calibration can take place on a wider time frame, but certainly bump testing, making sure that the thing's doing what it's supposed to do for you before every shift is crucial.
Okay. We had a couple questions about how the environment can affect some of these devices. Can monitors be used outside or in inclement weather, and how do portable monitors withstand caustic chemicals? Does it have any effect on either how long they can last for? Does it have any effect on their ability to accurately monitor the conditions?
Yeah, I mean, I'll answer that, I guess, in general terms by saying that all monitors are not equal. There are certainly some that are going to react more negatively with respect to caustic chemicals and more negatively with respect to typical environmental conditions. There are some that will not be rated to IP ratings that are consistent with either ingress of water or ingress of dust that can affect the performance. So that's something that you need to check. What is the IP rating of your instrument before you go to work with it? The other thing to check again is really just there is a difference, and again from manufacturer to manufacturer with respect to the sensor quality, how the sensors have been engineered within a particular monitor. It does vary greatly. And so some situations you might have a less expensive monitor, but those sensors are either going to malfunction in certain environments. Weather is going to affect them negatively. High humidity could be an issue for some sensors in some situations. So again, over time, you're going to start to understand that you're often going to pay a little bit more and get a better monitor and a safer monitor for your work, rather than spending less for something that isn't going to be as reliable. But again, taking a look at the IP rating of anything is going to give you a pretty good indication of how stable something's going to be depending on environment. And then talking with the manufacturer and asking them about the reactions to caustic chemicals, for example, is an important step to take as well. Anyone who's using something should be as highly educated about what type of safety levels it's going to provide. And so I would also encourage anyone who's using a monitor to get that information either straight from whoever they can, whether it's the manufacturer, the distributor they're working through, to ensure that it's not going to be affected negatively during a working situation.
Great, thank you. Could you discuss hazards and controls for attic or crawl spaces as confined spaces?
Well, I'm not sure if I understand the question completely, but I'll take a wild stab at it. Again, this is something that can vary depending on if you're talking about a typical household environment. I mean, hazards are going to not necessarily be present as they would be in an industrial environment. You might see, obviously, you might need some basic respiratory protection like a dust mask to prevent insulation from being inhaled. There might be other types of vapors of some sort that exist, but that's really going to be completely dependent on, on the age of the home, on what type of things have been stored, obviously deterioration of any sort of building materials that exist within a confined space. I think the best advice would be to make sure you have a basic respiratory protection, and if there's any risk or any thought that there might be something else within an attic or a crawl space, again, with respect to, I don't know, whether it could be radon, could be, again, paint fumes that have accumulated in the back. Take steps to identify what way you can test for that before you go in. And it could be something, Draeger, of course, manufactures detector tubes in several hundred different types to detect for different things. So, you can do a spot test with a tube to make sure that you don't need any additional protection. Or you could go something as sophisticated as a personal monitor with a pump or something on it to try to take an air sample before you enter that space. But again, it really is kind of up to the expectation of what you think you're going to encounter and being prepared for that ahead of time. I hope that answers the question, but it's pretty open-ended, so that could go in a number of different directions.
And I think like a lot of the things that we've discussed, it really is going to be site-specific, kind of the hazards that you encounter and the steps that you take, correct?
Yeah, and that's exactly, and that's what makes you talk about specific hazards that occur in confined spaces, and to your point, we can talk in general terms about what we might see and things that might occur. And obviously, the idea of this presentation was to say, well, there are things that if you do go into any confined space, regardless of hazard, you need to have something that's going to tell you accurately what's present and alert you accurately and fast and loudly and visibly to get out of that situation. But yeah, at the end of the day, it is a case-by-case basis, and if you're taking appropriate steps ahead of time to identify what some of those issues might be, you're going to be set up to have a safer project or a safer work area. But yeah, it is definitely site-specific, and it's very open-ended with respect to what types of hazards might exist in any given space.
Okay. Well, we have a question in here about gas monitoring. If you have forced intake air into a confined space through powered fans, do you have to gas monitor? Is that required?
Well, I don't know that it's necessarily required. It might be. Again, that's one of those things. I don't know that there's an exact answer. I think that would depend on a number of different variables. I think there could be state, local regulations. There could be OSHA regulations. There could be NIOSH situations. I mean, there's a whole slew of different questions that would come up that, again, make it difficult to answer that question just on that alone. It's quite possible that you've created with that air intake a very safe environment, but that doesn't necessarily mean you wouldn't also require gas detection. Or I should say you wouldn't want gas detection. I think there might be some people that would be hesitant to wear supplied air breathing apparatus for various reasons, either because they don't have room to wear it or whatever, or it's uncomfortable, which shouldn't be an excuse, but certainly there are those people that feel that way. But there aren't many reasons why you should outright dismiss the idea of gas detection. Even a multi-gas monitor is only going to set you back several $100s, and it's really not. It's not intrusive. It's not invasive. It doesn't get in your way when you're trying to work. So, I don't know. I guess my answer to that would be, you should never look for reasons not to wear a gas monitor or detect for a gas monitor. You should always make sure you have more than what you need. I'll put it that way.
Okay, great. We have time for one last question real quick. Can you comment on whether a non-standard work permit would count as a confined space entry permit?
Non-standard work permit. More than likely it would not. When you're talking about a permit required, it's going to have to be issued by a safety professional, someone that's familiar with the hazard, someone that's familiar with the degree to which someone might be exposed to a hazard in a confined space. So typically you're going to have a different type of permitting process that would exist when you're talking about a permit-required confined space.
Okay, great. Thank you. Unfortunately, we have run out of time. I apologize we didn't get to everyone's questions, but all of today's unanswered questions will be forwarded on to our speaker. Once again, I hope you take the time to fill out the evaluation survey on your screen to give us your feedback, and that ends today's Safety and Health Magazine webcast. I'd like to thank Rob, Draeger Safety, and all of you who listened in. Thank you, and have a great day.